So we'll start this second video on the Laplace transform by a very important theorem that allows you to link convolution and the Laplace transform. Remember that when you're given a impulse response of the system h of t and that you want to compute the response to a signal x of t, well, you can do this by saying that y of t, the output, will be the convolution, and this is how we write it, of the impulse response with the input signal. This is not very interesting. What is interesting is that you should know that you can write it like this: ht minus tau d tau. This can be really painful to compute in the time domain. So this is why it's important to see that and to know that the Laplace transform of a convolution between two signals, this is y of t, by the way, so the Laplace transform of the convolution of two signals is simply the product of the Laplace transforms of the underlying signals. So the Laplace transform transforms a convolution into a product, and this is really handy because now you can use that to, well, compute the response of any signal. So if you're given h of t, the impulse response, you'll take the Laplace transform and we'll call that the transfer function. You take x of t, the input, you take the Laplace transform, and this will be x of s. And you know that taking the convolution in the time domain is simply writing a product in the Laplace domain, so you'll have h of s, x of s. Okay, so you have the Laplace transform of y of t, and then the only thing that you have to do is take the Laplace transform inverse and you have the resulting response. Okay, and this inverse Laplace transform will involve partial fraction expansions and knowing your table of Laplace transforms. So the proof is given in the slides, although it is very tempting to see it and to go into the details. We'll leave it for your information. So the principle that I have explained previously is explained here maybe in a more visual way. So suppose that you're given the impulse response of a system. It's a characteristic of the system, and you want to have the response of this system to an input signal x of t. What you can do is compute the convolution, right, of these two signals, and you do this by staying in the time domain, and here is the convolution integral. Okay, so the other way, and in many cases it will be easier, is just to first do a Laplace transform, obtain the transfer function and the Laplace transform of the input signal, then do the convolution. But in the Laplace domain, convolution is really easy. It's simply taking the product, and then you obtain y of t by a inverse Laplace transform, and this will involve partial fraction expansions and knowing your tables of Laplace transforms. So we've just seen that y of s, okay, that's the Laplace transform of y of t, can be written as h of s times x of s, and this thing here is the Laplace transform of x of t, right? We've seen also that the transfer function is the Laplace transform of the impulse response. So this one over here is the Laplace transform of the impulse response. Okay, so h of s can be written as, well, you can see it from this equation over here, as y over s divided by x over s. Okay, so it's the Laplace transform of the output signal divided by the Laplace transform of the input signal. So we write it here as h of s because we make the link with the impulse response. Okay, by writing the transfer function as h of s, we say, oh, well, it's the Laplace transform of h of t. In other courses, in other references, you might see p of s, and there, well, the people that have written the transfer function put the focus on process. Well, this is the transfer function of the process. Okay, so the transfer function is called transfer function because it transfers the Laplace transform of the input to the output, and this transfer function is a characteristic of the system, and you can characterize the system by the poles and zeros, and the poles, well, they have a certain link, as we will see, with the impulse response, and it's an important tool for the analysis and synthesis. When we talk about synthesis, it's control design of systems and controllers. So there's a question that I like to give you at the time of the exam, and it's the following. Suppose that we're given a system and we know that the response to the input x1 of t is y1 of t. Okay, that we know that the response to the input x1 of t is y1 of t, and then we say, well, we want to have the response of this system to another input, and we'll call it x2 of t. This is what we're asked. So how are we going to proceed? Well, obviously, when you say that a system when given the input x1 of t produces y1 of t, you have enough information to characterize the system. So by this thing over here, we know that the transfer function will be y1 of s divided by x1 of s, right? So now we want a response to this one. Okay, we know h1 of s, so what we need to do is compute x2 of s, and we know that y2 of s is simply h of s times x2 of s. Okay, we can plug this thing in, so it's y1 of s divided by x1 of s times x2 of s. And once we have y2 of s, we can obtain the response by simply using the Laplace inverse transform of y2 of s. And this is the way you proceed. This is exactly using what is given here in this slide. So now that we've talked about the transfer function, we can look at the difference between a transfer function and the transform of a signal. So if we take, for instance, 1 over s, well, 1 over s can be the Laplace transform of a step input. Okay, if the x of t is a step, well, its Laplace transform is 1 over s. So this means that in this case you have a system and you would like to know the step response. Okay, so 1 over s will actually be here x of s. Okay, but 1 over s could also be the transfer function of a system. And if h of s, okay, is 1 over s, well, it means that this h of s is the Laplace transform of the impulse response, okay, and it means that this impulse response must be a step, okay. So this system with transfer function 1 over s is such that if you put at the input an impulse, okay, what you will have at the, and this is x of t over here, what you'll have at the output, this will be y of t, is a unit step. So such a system is called an integrating system. It's kind of obvious. Why? Because the unit step is the integral of the Dirac impulse. We have seen this at the start of the course. So you all know an example of an integrating process, and it's given here in French, Cuvier. Let's for instance take the example of a glass of water. So you can do the experiment when you finish this video. You go to the water tap, you put a glass below the water tap, and what you do to emulate a impulse Dirac, you open the tap and very quickly you close it. So what will happen, there's a little amount of water that will come in your glass, and the level in the glass will go up as a step signal, okay. Well, that kind of system, okay, filling a glass, filling a tank, a surge tank, has an integrating process characteristic. Now we can start combining both. Suppose that you have a system that has transfer function 1 over s, so it's an integrating system, and that you put at the input, well, a step input. Well, then you see immediately that y over s is the product of the two, 1 over s squared, Laplace transform inverse, and since you're very good at it now, you know that it's equal to a ramp signal, okay. So this is a second experiment that you can do when you finish the video course. You go to the water tap, you put your glass below, and what you'll put here at the input is a x of t this time, that is a unit step. Okay, so what you do is open the tap to a given position and then you leave it there. And what will happen, of course, at the output is that you'll see, well, a ramp at the output. That is to say, something that will go like this. Okay, so the relation, and again it's the integral of the input, so the relation between the position of the tap and the level in the glass, well, in between you have an integrating process. Let us look at another example, and let us have a look at this function of s. Well, it can be the Laplace transform of an input signal, okay, and in this case the input signal is a sine, okay, and this input signal you can put it at the input of a system, and in this case it's a x of s. But this quantity, this function of s, can also represent the transfer function of a system. Okay, so it's a system which has impulse response, which is a sine. Okay, so when you think about it, such a system is easy to find. It's a pendulum. Okay, if you put at the input an impulse, what the pendulum will start to do is, well, kind of oscillate, right? And if you look at the angle of oscillation, it will follow this kind of relation. Okay, so if this can be the transfer function of, for instance, a pendulum system. So let us have a look at this function of the Laplace variable s. Well, it can be the Laplace transform of an input signal that looks like this, and it's a damped sinusoidal input signal. Okay, it could be that you want to have the response of a system to this damped sinusoidal signal, but it could also represent the transfer function of a system, and in this case it would be a system with impulse response that is a damped sinusoidal signal. And what system would have that kind of behavior? Well, of course, a pendulum, but a pendulum with friction. Okay, so if you put an impulse to this pendulum, okay, it will start oscillating, and the angle will follow an equation like this. So it will be an exponentially decaying signal that is modulated by a sine. Okay, so depending on the situation, a function of a certain variable, a certain function of a variable s might be the Laplace transform of an input signal, or it might be a transfer function. So we continue this second video on the Laplace transform by considering stability in the Laplace domain. And remember that a system is characterized by its impulse response. Okay, so we'll denote the system by H, and if we put an impulse at the input, we have the so-called impulse response of the system. Okay, and what we can do is go to the Laplace domain, and we end up H of s, and we'll see pretty soon that this is the, well, transfer function. Okay, for the moment we'll just say that it's the Laplace domain of the impulse response, and of course the associated Laplace transform as a region of convergence. Okay, and we have seen that the region of convergence can be defined as follow. It's OS such that this integral converges here. Okay, so we have an integral with the h inside, well, multiplied by an exponential. We take the absolute value and then we integrate. This integral should be bounded. Okay, so h of t is defined, it's the impulse response, and now we look at the region of convergence of the Laplace transform of the impulse response. So that's one thing that we've seen previously. In section 3 we also have considered stability, but in the time domain, and we have seen that a causal linear time invariant system with impulse response h of t is stable if and only if its impulse response is absolutely integrable. So this means that this integral over here is bounded. Okay, so this is another important aspect of what we have seen previously. And you should note that if the region of convergence contains sigma is equal to 0, okay, if you put sigma is equal to 0, this becomes a 1 over here, and you end up with this condition over here. So if the region of convergence includes sigma is equal to 0, then, well, the resulting transfer function will be one of a system that is bibostable. Okay, if the system is bibostable, so this condition must be satisfied, then sigma is equal to 0 must be in the region of convergence of h of s, because this integral is bounded, and sigma is equal to 0 must therefore be in the region of convergence. So we arrive at the stability condition in the Laplace domain, which says that a causal system is stable if it is described by a transfer function h of s, and remember that h of s is the Laplace transform of its impulse response, and that this transfer function h of s has a region of convergence which includes the imaginary axis. So sigma is equal to 0 is in the region of convergence. This comes from what we've seen in the previous slide. For a causal system, this condition implies that all the poles of the transfer function h of s are strictly in the open left half s-plane, and this is what we'll see now. So remember that to obtain the region of convergence of the transfer function, what we'll do is consider all the poles, and we'll consider the poles with the maximum real part, and we know that the region of convergence is to the right of these poles with a maximum real parts. So if all poles are to the left of the imaginary axis, okay, well, obviously the region of convergence will include sigma is equal to 0, and the imaginary axis can also be written as sigma is equal to 0, right? So in this case, the system will be stable, and we can see here that all the poles are to the left of the imaginary axis. If the system has poles to the right of the imaginary axis, well, the region of conversion will be to the right of these poles, okay, and obviously it will not contain sigma is equal to 0, which is also the imaginary axis, and by definition the system will be unstable. So we have seen that if all the poles are strictly to the left of the imaginary axis, the system is stable. We'll even call it asymptotically stable. And then we can ask the question, what happens if, well, there are poles on the imaginary axis, and we can see two cases here. If we take the Laplace transform of the unit step, well, it's 1 over s, and if you take the Laplace transform, for instance, of a sine omega 0 t u of t, this will be omega 0 over s square plus omega 0 square. If you look at the Laplace domain, so sigma over here and j omega over here, we'll take this one in blue over here. Then we have a one pole at the origin, and it's situated on the j omega axis. So this is not this signal is not asymptotically stable. We'll call it marginally stable. And don't forget, in the time domain, if we show the step, we have the unit step, so we have something like this. This is 1 over here. It's not stable, asymptotically stable, in the sense that it goes to 0, but it does not grow unstable, so we'll call it marginally stable. Okay, This is one pole on the imaginary axis. The other example here is two complex poles on the imaginary axis. So you have j omega 0 here minus j omega 0 here. If we look at this in the time domain, so we'll have something like this, and then it starts like this. Okay, so again, it's not asymptotically stable, okay, but it's not a signal that is growing. So again, we'll call this type of signal marginally stable. Okay, so this is again with a complex pair of poles on the imaginary axis. So if you have one real pole or a complex pair of poles on the imaginary axis, we'll say that the system is marginally stable. So what would happen if you would have two poles on the imaginary axis? And an example of that is the Laplace transform of t u of t. Okay, that's a ramp. Okay, and you know that it's 1 over s square, and there you have two poles at the origin, and clearly having two poles on the origin will lead to instability. Okay, there is something similar. I won't go into the details. If you have several complex poles on the imaginary axis, this will also lead to instability. So as a conclusion, if you have one real pole or a pair of complex conjugate poles on the imaginary axis, but just one pair, then the system is marginally stable. If you have one or several poles to the right of the imaginary axis, or several real or complex conjugate poles on the imaginary axis, the system will be unstable, and well, the responses will grow as t tends to infinity. So let us come back to the stability in the Laplace domain and this Laplace transform of an exponential signal, and a comment that I've made at the beginning of the course when I spoke about the usual suspects. Okay, so let us consider the Laplace transform of the exponential of t u of t, and then I see students hesitating. Well, it's 1 over s, and then the question is it -1 or +1? Well, in view of what we have just seen, we know that it is -1. Okay, so this is clearly a causal function that is growing, so its Laplace transform should have a pole in the right half plane. So this is correct because the pole is indeed equal to 1. It's in the right half plane. And similarly, the Laplace transform of e to the minus t u of t is a signal that is asymptotically stable. When t goes to infinity, this will tend to 0, so we know that it must be 1 over s plus 1. We have a pole at -1 in the left half plane. So you should not make mistakes. Okay, if you remember the stability in the Laplace domain, things become a lot easier. Well, it's well known that control engineers have a lot of humor, and therefore a little control engineering joke. I'll leave you a few seconds to read it, and it might help you to remember this stability theorem in the Laplace domain. So these are two Laplace transforms that you'll find in your table of Laplace transforms. Simply the Laplace transform of an exponential. Okay, so this is this result over here, and the Laplace transform of an exponential modulated by a sine, and the Laplace transform is given over here. Remember that in this case the pole is at p equals a, and here the poles are complex conjugate poles, and they are at sigma 0 plus minus j omega 0. This is not a surprise. Remember the link that I have made with complex exponential signals that you've seen in section 2. There is something similar here when you have e to the sigma 0 t cosine omega 0 t u of t, and in this case you would have s minus sigma 0, and the denominator would be exactly the same, so you would have the same poles. Okay, so what can we draw as a conclusion over here? That a system, and we're now talking about a system that would have transfer function that would be this one or these, one of these two, right? It has obviously poles at a in this case, and at sigma 0 plus j omega 0. Well, the underlying impulse response of that system, okay, well, the impulse response from the transfer function is simply Laplace inverse, is given by these functions over here. Okay, so if the transfer function is this one, the impulse response is this one. If the transfer function is this one, well, the impulse response is this one. So we can now start looking at pole locations and look at the corresponding impulse. Okay, so if A is positive over here, we have a pole on the right side of the imaginary axis, so you will have a growing exponential. If A is negative, well, you'll have a decaying exponential, right? This kind of signal is an exponential that is modulated by a sine or a cosine. If the real part of the pole, sigma 0, is negative, well, you'll have a decaying exponential. If the real part is positive, right, we'll have a growing exponential. So there is a clear link between the poles of the transfer function and the, well, behavior of the impulse response, and we'll show this in the next slide. So let's have a look at the dynamic behavior that you can have as a function of the pole location. So if we look on the real axis, we have to remember that the Laplace transform of this signal over here is equal to 1 over s minus a. So in here the a is positive, so you have indeed a growing exponential. Here a is 0, so, well, e of 0t, that's of course 1, and so you have a system that has as an impulse response a unit step, and these systems are called integrator systems because the impulse response, which is a step, is the integration of the input signal, which is the Dirac impulse. And if a is negative, okay, well, then you have a pole on the left side and you'll have a decaying exponential. So let us now consider the cases where the poles are complex conjugate poles, and there we have to consider, for instance, the Laplace transform of e to the sigma 0 t sine omega 0 t u of t, and what we obtain, or what you obtain after, well, using the properties of the Laplace transform, is s minus sigma 0 squared plus omega 0 squared. Okay, so the poles are at sigma 0 plus minus j omega 0, and if you have, instead of a sine over here, a cosine, well, instead of the omega 0 you'll have s minus sigma 0. But in any case, the poles are the same. Okay, so if you have complex conjugate poles, and if the real part is positive, and this is this case over here, you have a system which has an impulse response which looks a lot like that. It's an unstable impulse response, and it's an exponential that is modulated either by a sine or a cosine. Knowing if it's a sine or a cosine will not depend on the poles, but will depend on the numerator, so it will depend actually on the zeros. If you have complex conjugate poles on the imaginary axis, this means that sigma 0 is equal to 0. Well, then you have, of course, a system which has an impulse response which is either a sine or a cosine, right? And if the complex conjugate poles have a negative real part, well, you have a decaying exponential that will be modulated by sine and cosine, or cosine, depending on the zeros that you have. So, knowing the transfer function h of s, right, and the pole location, you can infer the behavior of, well, the impulse response. Please do not study this by heart. You have to make the link with the Laplace transforms, okay, that are in your table, and these you should be able to find them back from the properties of the Laplace transform, linearity properties, frequency and time shifting properties. Okay, so this is really important. So in the next few slides we learn about the initial and final value theorems, and the idea is here that you want to obtain information about y of t in the vicinity of 0, or when t is going to go to infinity. That's for the final value theorem, and you want to do this given y of s. So one way to obtain this information would be to compute y of t is equal to the inverse Laplace transform of y of s, but in many cases this is going to be, well, some computations might be heavy, so sometimes we are only interested in the information in the vicinity of t equals 0, or when t tends to infinity, and we don't want to go through the trouble of computing this inverse Laplace transform. So there is a theorem that tells you how you can obtain the value of y in the vicinity of 0. Well, here we assume that y of t and its derivative have all Laplace transforms. These are the assumptions, and then, well, the limit when t tends to 0 plus, well, it's slightly to the right of 0. We assume that this limit exists, and when it exists, well, it can be obtained as follows. So y in the vicinity of 0, it's simply the limit when s tends to infinity of s times the Laplace transform of yt. This is ys. Okay, so here you want the information around t is equal to 0 plus. Okay, and you know that there is an, well, inverse relation between time and frequency, so it does not come as a surprise that you should take the limit when s tends to infinity. So similarly, it's possible to obtain the steady state value of y of t, that is the value of y of t when t tends to infinity. Okay, and you can obtain this y of t without taking the inverse Laplace transform of y of s, and you do this using the final value theorem. Again, there are assumptions, and the assumptions are that the poles of sys are to the left of the imaginary axis, so all poles of sys are in the left half plane, and when you meet this assumption, you can compute the steady state value of y of t, that is the limit when t tends to infinity of y of t, and this steady state value is the limit when s tends to 0 of sys. Notice again this inverse relation between time and frequency. Remember that s is equal to j omega, so when time tends to infinity, well, the corresponding s is of course tending to 0. So coming back to this final value theorem, and to kind of show you that it's important to take the assumption into account, because if you forget it, you can draw the wrong conclusion. So let us take an example of a exponential function, and it has, well, Laplace transform 1 over s minus 1. Okay, it's correct, it's unstable. Okay, and you have a pole to the right. You cannot kind of see what is happening with y of s, if you call this y of s, and you cannot use the final value theorem. Okay, so for instance, if we would use it over here, we would have that the limit that t tends to infinity of y of t is the limit of s tending to 0 of the quantity sys, so it's s over s minus 1, and it is 1. Okay, so if we use in this case the final value theorem, we get the impression that the steady state value is 1, whereas we know here that this signal will never converge. Okay, and why can't we use and draw this conclusion? Well, it's because this assumption is not satisfied. You see here that s times this transfer function has a pole that is to the right of the imaginary axis. So please do take this assumption into account. It's not a little detail. So here's an application example of this initial and final value theorems, and we're going to apply it to have an idea of the step response. You know that we put here a step input to, and the step response to a system that is characterized by this transfer function. Okay, we will not cover this system in this course. It will be covered in subsequent courses and by my colleague David Rochard. And this system is called a lead lag system. So since you don't know that system, well, maybe it's a good illustrative example to use it in order to obtain an idea of the step response using this initial and final value theorems. Okay, so the response, it's easy to obtain. You just take the transfer function and you multiply by the Laplace transform of the input. This is what we obtain. This is the Laplace transform of y of t, the step response of this particular system. So what I could do, of course, is compute the inverse Laplace transform of this, but I'm a bit lazy here and I would like to have an idea of this y of t without taking the inverse Laplace transform. So what we'll do is use the initial value theorem, okay, to have an idea of the step response in the vicinity of 0. And what we have to do is, well, take this one, multiply by s, so this means that this one will cancel out here, and take the limit when s is going to go to infinity. So it's the limit when s is going to infinity of k t1s plus 1 t2s plus 1, okay. And you remember, if s is going to take large values over here in the denominator and numerator, it's as if you can forget this 1 over here, and you can see that the limit will indeed be k t1 over t2. We can also have a look at the steady state response, okay. This is the response when t is going to tend to infinity of y of t, right? This should not write, should it be write it between quotes. Formally I should write things like this. And if I use now the final value theorem, I can use the final value theorem if the pole is in the left half plane. So implicitly we make the assumption here that t2 is positive. Otherwise the system would be unstable and it would make no sense at all to compute the steady state response. So let's take this limit over here, and it's the limit as s tends to 0 of k t1s plus 1 t2s plus 1, and this is indeed k, right? So let's have a look at the step response. So this will be our reference frame t, and this will be s of t. Remember, s of t denotes the step response. So this will be here our input. It will be a step, so we have a 1 over here, and we'll have to consider different cases, okay. So we know that when we arrive at steady state, well, will be let's say that we have a gain of 2, so we'll be stabilizing somewhere in here, okay. So this is 1 over here because it's the input, and this is k, right? So this we know from the final value theorem, and we see here from the initial value theorem that this system reacts immediately to a step response, okay. And we know that it is reacting as follows. So depending on t1, we'll have different responses. So let's maybe consider the case where t1 is smaller than t2, okay. So what will happen is something like that. It's a causal system, causal input, so it does not react before t is equal to 0. And since t1 is smaller than t2, well, kt1 divided by t2 will be smaller than k. So let's take this value over here, and from there on it will look something like this. Okay, so this is a typical response when t1 is smaller than t2. Let's take an example where t1 is larger than t2, okay. So of course in here you see that kt1 over t2 will be larger than k, So we'll have a response like this. Okay, so this is a typical step response of this lead-lag system when t1 is larger than t2. And what could happen also is that t1 is negative. Okay, so then what would happen is that you have a so-called inverse response. So this is the step response of such a system when t1 is negative, and it will look like this. Okay, so by using the initial and final value theorems, you can, well, kind of determine the step response of this lead-lag system that you did not know up front without actually computing the inverse Laplace of y of s. The static gain of a system can be obtained by considering its transfer function at s is equal to 0. So this is how you obtain the static gain of the system, and it kind of tells you the ratio between output and input under steady state conditions. Steady state means when all transients have disappeared. So let us assume here that we have a signal, okay, x of t, that is equal to x0 u of t. So x of s will be x of 0 divided by s, right? And the output will be h of s times x0 divided by s. We can now compute, and this is called y0 over here, maybe not the best name, the limit when t is going to infinity of y of t, and this is the limit when s is going to 0 of s y of s. So this will be the limit when s is going to 0 of h of s x0. So this is h0 x0. Okay, so the relation or the ratio between output and input is indeed h0 at steady state. We'll see this later, but the transfer function can actually be viewed as a generalization of the concept of a gain. Okay, so in this subsection we compute the inverse one-sided Laplace transforms, and this is where we are going to use the table that we have constructed before. And what we assume here is that we're given a function of the variable s, a rational function. Okay, so it can be written as a numerator polynomial over a denominator polynomial. Both polynomials will be polynomials in s, and the coefficients will be real valued in the practical applications. Okay, so what we'll have to do is, well, factor the denominator and do a partial fraction expansion. You have done this in previous courses. We'll review this later, but before we do the partial fraction expansion, we need to ensure that this f of s is strictly proper. Okay, this means that the relative degree, okay, so the degree of the denominator minus the degree of the numerator must be at least 1. If this is not the case, you cannot do the partial fraction expansion because it will lead to incorrect results, and if f of s is not strictly proper, you'll have to do a so-called Euclidean division, so that you decompose f of s in a certain number of terms and into a new rational function where the degree of b is indeed less than the degree of d. Okay, so let us do an example. Suppose that f of s, I will take a very simple example, is s plus 2 over s plus 1. Then it's pretty obvious that you cannot do the partial fraction expansion, okay, because this f of s is not strictly proper. So what you have to do is the Euclidean division. So let's do this. So what we do is divide the polynomial s plus 2 by the polynomial s plus 1, and we can see that it will enter 1 times. So we have s plus 1 here, we subtract and we end up with 1. Okay, so this means that this one can be written as 1, but there is a rest over here, so plus 1 over s plus 1. Okay, so you see here that you have obtained here now a strictly proper rational function. Okay, here you don't need to do any partial fraction expansion because it's already in its, well, simplest form. And please check, if you do a Euclidean division, if the result is correct by putting everything back on the same denominator. And indeed this is correct, because if you put it on the same denominator, you have s plus 1, you'll have s plus 1 plus 1. So indeed this is correct. So here are the general ideas. The poles of f of s provide the characteristics of f of t, and more in particular, if f of s is the transfer function, the poles, well, they are the essential characteristics of the system, and we've seen this before. Okay, so f of s will be written as a rational function, and you'll have a numerator polynomial and denominator polynomial. The coefficients will be real, and the roots of these well, numerator and denominator will be real or complex conjugate, and the roots and 0 can be simple or multiple. Okay, so here in what follows we'll of course focus on the roots of the denominator, the poles of the system. Okay, so the idea will be to do a partial expansion of f of s, to decompose everything in, well, elementary irrational components, and then you can, well, use your tables to find the inverse Laplace transform. Okay, so in these inverse Laplace transforms, do not forget the u of t. It should be included because the result of the inverse is causal and it's integral part of the inverse. Some of these rational components might even include something times e to the minus tau s, and then if you do the inverse Laplace transform, it will include a step, okay, but it will be a step that is time shifted. Okay, so that's also very important. So before we talk about partial fraction expansions, I will talk about roots and factorization of a polynomial, because in the partial fraction expansion you'll need to factor the polynomial d of s, and to factor it you'll have to compute the roots. Remember that the roots will actually be the poles of the system. Well, the roots are the values such that if you plug this in to the polynomial d, you obtain 0. And if d of s is of degree n, well, you'll have n of these roots, n of these poles, and this denominator polynomial d of s that takes this form in general, well, if you have the roots you can factor it as follows. I want to make sure that you see what I mean by this, so I will write it like this: s minus p1, s minus p2, up to s minus pn. Okay, and what I often see is that this coefficient here, dn, that is in front of the highest power of s, is forgotten. Okay, it's kind of obvious that if you multiply all these little factors here, well, the power will be Sn, and if you forget this one, you have a mistake. Okay, so please, when you factor the polynomial, don't forget this factor over here, dn. So let us start with partial fraction expansion in the case of simple real poles. So we assume here that d of s has only simple real poles, so that the roots of d of s are simple and real. Okay, there is of course this coefficient dn from the previous slide, but we assume that it is either 1 or that we have, well, divided the numerator by this dn. Okay, so you end up with this expression over here, right? So what you can do now is do the partial fraction decomposition. So you'll write it as a sum of terms that look like this, and here you have, well, the corresponding poles, and this is a coefficient that needs to be computed. Once you have this partial fraction decomposition, well, you can obtain the inverse Laplace transform, because you know that the inverse Laplace transform of 1 over s minus pk is equal to e pkt, and I should not forget to put the unit step to make everything causal. Okay, so this is how you go from here to here over here, and remains the question of how are you going to compute this expansion coefficients. Well, for the term corresponding to pk, what you simply do is take f of s and multiply by s minus pk. Okay, so this means that it is product s minus pk will disappear, and then you evaluate this in s is equal to pk, and you have the corresponding expansion coefficient. Well, let us take an example, and we'll take the following example. F of s is equal to s plus 1 divided by s squared plus 5s plus 6. So the first thing that you have to do is, of course, factor the denominator. Okay, so it will be s plus 1 divided by, okay, you see that the sum of the roots, it's a 5 here, so, and here the product is 6, so it must be s plus 2 over s plus 3. This seems to be correct. How can I know that it's correct? Well, I expand this and I should obtain this again, so please do check this. So the partial fraction expansion, I can write it like this. It's a over s plus 2 plus b over s plus 3. A general rule is that if your denominator is of the second order, you should have 2 constants, and this is okay over here, so might as well start using this. Okay, so a, if we look at this, well, you take this one and you multiply by s plus 2. Okay, so it's as if you're hiding this one over here, so it's s plus 1 over s plus 3 evaluated at the root, and the root is s is equal to minus 2. Okay, So if you have a look at that, it's minus 1 over 1. So this will provide me with a minus 1 over here. Okay, so B, if you look at this, you need to multiply this one by s plus 3. So we are going to hide this one. And what remains is s plus 1 over s plus 2. Evaluated at the root here, at the pole, is s is equal to minus 3. So this will yield minus 2 over minus 1. So it's a 2 over here. Okay, so this means that we can write f of s as minus 1 s plus 2 plus 2 times s plus 3. Are we ready? No, we're not, because we need to check if everything is correct, right? So what we do, we put it under the same denominator. So this will give me minus s plus 3 plus 2 times s plus 2, right? And this will, if you check, minus s plus 2s, it's an s, minus 3 plus 4 s plus 1, s plus 2, s plus 3, and now we're satisfied because we have checked that everything is correct. Remember the usual suspects, the faults that I see at the exam, it's factoring, okay, without check and a mistake. Then compute partial fraction expansions without checking the result and mistakes. Okay, so this is very important that you do this. So the next case is the case with simple complex conjugate poles, and you can see over here that the poles are sigma 0 plus minus j omega 0. So we have a second order denominator polynomial. Usually, of course, you will not find it in this form, yes, but you can obtain this form by completing the squares. Here we have a numerator polynomial, and of course we need f of s to be strictly proper, so n of s is of degree at most n. So we can proceed just as we did with real poles and write the, well, partial fraction expansion. And here a is in this case a complex number, and here we have its conjugate, right? So you have two unknowns, k and phi here, and this makes sense because the denominator is of the second order. And then you can take the inverse Laplace transform. I'll leave you the details. Well, this method using complex calculus is maybe not the best way to obtain the partial fraction expansion, as we will see. Well, the easiest way, well, that's my opinion at least, is to rewrite the numerator and express it as follows, okay, with two constants a and b. So this will be n of s, and if you rewrite it like that, you can decompose it into the sum of two terms. Here you see that we have put an omega 0 over here, because now you recognize that this is the Laplace transform of a sign that is multiplied by an exponential, right? But you see here, if you can cancel the omega 0 with the omega 0 over here, so you have the a, this one, and in here you have the second part of the numerator, okay? And the reason why we write it like that is, of course, that this is the Laplace transform of a sine multiplied by an exponential, and here we have a cosine multiplied by an exponential, and very easily you obtain the inverse Laplace transform, and you don't have to do any complex calculus. So let's apply this and let us find the inverse Laplace transform of this rational function over here. So the first thing that we do is, of course, factor the denominator, and here what we can do is construct a square based on s squared plus 2s. Okay, and you see that you have s, double product is 2s, so we need s plus 1 squared. So 1 squared, and this leaves us with 3 that you have to add. So you can immediately see here that the poles are complex, the poles of this part here. So you have a pole at 0, and the two other poles are at -1 plus minus square root of 3j, right? So indeed we fall in the case of the previous slide. If you have, of course, two real roots, well, you have to use the method with the real poles. Okay, so what we'll do is use this partial fraction expansion here. So we'll leave the denominator as is, and since we have a third order here at the denominator, we need 3 constants. We need one for this term over here, and we'll need 2 of them for this term over here. Okay, so to compute a, well, we can use the method that we've used when you have a real pole, and you have indeed here a real pole. So a is obtained as follows, and if we hide this one over here and we replace s by 0, indeed we have a 1 over here. And one way to obtain b and c is to put everything back on the same denominator and compute the numerator. We know that the numerator is 4, and we obtain this thing over here. So looking at the terms in s squared, we have a plus b is equal to 0, and looking at the terms in s, we have 2a plus c is equal to 0. We know that a is equal to 1. Okay, so this leaves us with b is equal to -1 and c is equal to -2. So this is what we have obtained. We had a is equal to 1, b is equal to -1, and c is equal to -2. So this is what we obtain. In our case, the sigma 0 is this one over here, and this is omega 0 squared. Okay, so we'll rewrite this in order to have a, well, sine, this one, and a cosine that is multiplied by in this case, a decaying exponential. Okay, in order to have that, well, here at the numerator we have to have a multiplier of s plus 1, since we have the minuses here have been put over here, of course. So since we have a 1 that is multiplying the s, well, we need to put s plus 1 at the numerator. This leaves us with a 1. Okay, so there's a 1 left, and since we want here omega 0 at the numerator, this is omega 0, well, we have to divide by omega 0 over here. So this is the Laplace transform of a cosine that is multiplied by decaying exponential, and this is the Laplace transform of a sine that has been multiplied by a decaying exponential over here. So if we do the inverse Laplace transform, this is the Laplace transform of a unit step, this is what we obtain. Okay, and don't forget, this u of t is integral part of the inverse Laplace transform. We have to make everything causal. Okay, let us consider the case now of multiple real poles. Okay, so again we assume that f of s is strictly proper and that it has multiple real poles. So this means that the degree of n of s is at most r minus 1. Okay, so when we do the partial fraction expansion, we need r terms, and here they are. Okay, so it makes sense. This is a polynomial of degree r, so we need r, well, coefficients to express the partial fraction expansion. And then when we do the inverse Laplace transform, this is what you obtain. This is one we have not considered in the course, in this video course. It's in the slide, so you can have a look, and its inverse Laplace transform is given over here. So in this video course I will, well, maybe stick to the case where r is equal to 2, okay, but you have the general formula here in the slides, and you can also find in the slides, well, the inverse Laplace transform and the explanation why it corresponds to this over here. Okay, so you remember that the inverse Laplace transform of this one is C2 t, and then the exponential u of t. This is something that we have seen, and we have obtained it by the frequency shifting property, if you remember. Okay, so now comes the question of computing C1 and C2. C2, it's easy. You take f of s, you multiply it by s minus a square, and you evaluate it in s is equal to a, so at the root. So this is the same as in this case here, n of s evaluated in s equal to a. Okay, this is what is indicated here. And now C1, well, here you have to take f of s multiplied by s minus a squared, take the first derivative with respect to s, and then evaluate it in s equals to a. So this is one method. It's rather quick. In previous courses you have seen other methods to obtain C1 and C2, for instance putting everything back at the same on the same denominator and then equating things and obtaining a system of equation and then solve for C1, C2. If you feel more comfortable with these methods, so please use these methods. This is here an alternative method that is proposed in the course. So let us take an example and well, obtain the inverse Laplace transform of this rational function over here. So we have a simple pole in 0 and we have double poles in -2. Okay, so if we write the partial fraction expansion, this is what we obtain. Again, third order polynomial, so we expect 3 constants. So for this one it's quite easy, right? This is just multiplying this one by s, so hiding this one and replacing s by 0, and this is what we obtain. For c it's quite easy as well, so what we need to do is multiply by s plus 2 squared, so it's hiding this thing over here, so we are left with 4 over s, and we consider it at the root here at the pole, and we obtain -2, right? And to obtain b, right, this is the C1 coefficient of the previous slide. What you have to do is multiply by s plus 2 squared, so hide this thing. We're left with 4. This is equal to 4 over s. We take the derivative with respect to s and we evaluate it in s is equal to -2, right? If you take the derivative here, we have -4 over s squared. We evaluate this in -2 and we have -1. So this is the partial fraction expansion that we have obtained once we have plugged in a, b and c. So now we have to take the inverse Laplace transform. So the inverse Laplace transform over 1 over s, it's a unit step. So here we have a exponential multiplied by this unit step. Please do not forget the unit step to make sure that the function becomes causal. And now we have to take the inverse Laplace transform of this one. So if we remember, or if we can find that the inverse Laplace transform of 1 over s squared is a ramp signal that we can write like this, then we can use the frequency shifting property to find the inverse Laplace transform of this one over here, and this, it will be this one multiplied by an exponential, so we'll obtain t e to the minus 2t u of t, and we can plug it in here, and we obtain, well, the following result. So we can now start the analysis of linear time invariant systems, and we know that a system that is of nth order will be described by an nth order differential equation. So it means that the highest derivative will be an nth derivative, and it will be described by such a differential equation. Okay, so x of t is the input of the system as usual, and y of t is the output, and there will be n initial conditions. So you'll have an initial condition on y itself, on its first derivative, and then you continue up derivative n minus 1 evaluated in 0, and you see that in total you have n initial conditions. Okay, so what you can do here is go to the Laplace domain, and if you could compute the Laplace transform of this equation and you rewrite it a bit, this is what you obtain. Okay, you have two terms, one that is coming from the input, and one where you have, well, kind of collected the influence of all the initial conditions. Okay, and you have two polynomials, b and a. You can kind of see what will happen, for instance, if you take the Laplace transform of this one. Okay, so you'll have b0 plus b1s plus bm_sm times the Laplace transform of x, and that will be x of s. Okay, so this is the polynomial b of s, and on this side, well, you can do the same. You'll have a0 plus a1s plus ansn times y of s, but here also there will be this dependence on the initial conditions, and this is how this is produced over here, but this will be a of s. Okay, so this is how we obtain the output in the Laplace domain. So this is the expression that we have obtained. Okay, and you see two terms in there, and if you of course compute the inverse Laplace transform, you obtain y of t, and again you'll have two terms, and the first one is what is called the zero state response. Okay, it's the response that you obtain if the initial conditions are 0, and it comes exclusively from the input, as you can see. We have seen this when we were talking about solutions of differential equations, but in the time domain, of course, if you use Laplace transform arguments to obtain the solution of your differential equation, but of course you'll encounter exactly the same terms. The second term over here, the Laplace transform, the inverse Laplace transform of this term over here, it's the zero input signal. It's the response when the input signal is 0, and it's the response that is coming from the initial conditions. Okay, so in French this is la réponse forcée, and in French again this is la réponse libre. Okay, so this one over here will be denoted h of s. This is the relation between the input and the output when the initial conditions are 0. So this is called the transfer function of the system. So it's probably the good moment to do a first example or first exercise of finding the solution of a differential equation. Okay, so here we have a second order differential equation because the highest derivative is a second derivative, so the underlying system is a second order system, right? So here we have the initial conditions, and we have two initial conditions as the system is a second order system. Okay, so here the input will be, well, this signal over here, so this will be x of t, right? So what we can do is maybe go to the Laplace domain, and before we go to the Laplace domain, we remember that the Laplace transform of the derivative of y is s y of s minus y 0. So here we use the initial condition on y at time 0, and we can also obtain the Laplace transform of the second derivative of y by remembering that it is s times, well, the Laplace transform of the first derivative minus the initial condition, but here the initial condition on the derivative. So what we can do here is plug that in this equation, and we obtain s times, well, sy of s minus y0 minus y prime 0. Okay, so here I need a parenthesis, so it's s square y of s minus y0 s minus y prime 0. Okay, if I do it this way, I cannot make a mistake. Okay, so let's write it over here. So we have s square ys minus y0 s minus the condition, initial condition on the derivative, plus the Laplace transform of this one, don't forget it, is y of s, and for the moment we'll just write x of s, right? This one will not give a contribution because it's 0, and this is minus 3. So what we'll have is, if we put all the, well, terms with a y of s, we'll have s squared plus 1 y of s minus 3 is equal to x of s. Okay, so now we don't need this anymore. We can remove this, and we can write y of s, and it's equal to 3 over s squared plus 1 plus 1 over s squared plus 1 x of s. So we recognize the two terms. Here we have the 0 input response, okay, the response that comes from the initial condition, and indeed we see that there is a response coming from the initial condition, and this is the 0 state response, the response that comes from the input. Okay, So in French, réponse libre, réponse forcée. And here we have the transfer function of the system. Okay, it's the relation between input and output when the initial conditions are 0. So this is an illustration of what we have seen before. So we can have a look at the Laplace transform of sine 2t u of t. So here omega 0 is equal to 2. So the Laplace transform will be omega 0. Okay, so it's 2 over here over s squared plus omega 0 squared. So it's a 4 over here. Okay, so what we obtain is the following relation. Okay, so it's 3 over s squared plus 1 x of s. Well, we have to take this Laplace transform, but we have a 3 over here. Okay, so we need 6 over s squared plus 1 and then s squared plus 4. Okay, so we can erase this and we have obtained an expression for y of s, and again this is the 0 input response and this is the 0 state response. And we remember that this was 3 times 2 over s squared plus 4. Okay, so what we have to do now is, well, this one is already a transform that you recognize, right? So why would you put it on the same denominator? This is what sometimes that I often see. For me, well, it's easier to take just this one and to decompose it as something with a denominator s squared plus 4 and another term with a denominator s squared plus 1. We have a 4th order, so I expect 4 coefficients, right? So 4s plus b, cs plus d, right? So let's have a look at that. We can have a look at the terms in s cubed. I will have a s cube and I will have c s cube, and I don't see any term in s cube over here, so I have a plus c is equal to 0. I can have a look at the terms in s. I will have a, okay, and I will have 4c, so a plus 4c is equal to 0 as well, because I don't see any term in s over here. So this will lead to a is equal to c is equal to 0. Okay, well, if you get a bit of experience, you'll see immediately that the terms in a and c, they will only make terms in s cube and s, and so since we don't see them over here, we can very easily conclude that these coefficients are all 0. So let's have a look at the term in s square now. So we'll have a, and we'll, sorry, not this, this is not correct. The a will not, and they will make terms in s cube and s only. So terms in s square will be b, and there will be d. So b plus d, and it's again equal to 0 because we don't see any term in s square over here. And then we have to consider independent terms in s to the 0, and what we see here is b, and we have 4d and this is equal to 6 now, because we see indeed an independent term. So if you subtract the first equation from the second, we obtain 3d is equal to 6, so d is equal to 2. From this equation we see that b is equal to minus 2 over here. Okay, so you can rewrite this as 3 over s squared plus 1, and then we have minus 2 over s squared plus 4. Okay, and we have, well, 2 over s squared plus 1. So we already have a term over here, so what we'll do is erase this one and put a 5 over here, right? So this is y of s, and now we can do the Laplace transform inverse, and we obtain y of t. Okay, so this one here with a1, well, that's the Laplace transform of sine of t. So we'll have sine of t times 5, of course. Okay, and here we'll have, well, this one here, well, that's the Laplace transform of sine 2t. So we have to multiply by the unit step to make the whole thing causal. Okay, are we finished? No, we're not. We have to check that we meet the initial conditions. So we see very easily that the first initial condition is met. Y of 0 is indeed 0. To see if the second condition is met, well, we compute the derivative, and that will be 5 cosine of t minus the derivative of this one. Don't forget there's a 2 over here, so we'll have minus 2 cosine of 2t, and the whole thing multiplied by t. So let's have a look at the value of the derivative in 0, and we have 5 minus 2, and this is indeed equal to 3. So now we're finished, and we're kind of sure that we didn't make any mistakes, because, well, we meet the initial conditions. So in this subsection we cover the frequency response of a system, and we assume that the system is subjected to a sinusoidal input with input frequency omega, and we look at the response of the system. If you look at the slides that I have skipped, these slides are there for your information. You can show that the response is composed of two terms. There will be a term that has, well, that takes into account the so-called transient, and the transient will be disappearing if the system is stable. Okay, and there will be the steady state response, and what you see here on the screen is the steady state response. That is the response of the system when it's subjected to a sinusoidal input and when all the transients have disappeared. And what you observe is that the output, the steady state output, is again a sinusoid at the same frequency. Okay, it is amplified. This is the K that I've used previously in the chord, and it has been shifted, okay, phase shifted over here. So this is not a surprise. The steady state response of a linear system when it's subjected to a sinusoidal input is simply a sinusoid at the same frequency that is amplified and that is phase shifted. Okay. Well, the nice thing about this equation is that we know now how to obtain K and how to obtain phi as a function of frequency. So the amplification is obtained by considering h of s at s equal to j omega and considering the magnitude or the modulus. Okay, and the phase shift is obtained by considering the transfer function again at s is equal to j omega. This will be, of course, a complex number, and if you consider the argument, well, you obtain the phase shift. And as we had said previously, well, the gain over here and the phase shift will actually depend on the frequency omega of the input. So you can view a linear system as a frequency filter. If you vary the frequency, okay, from 0 to infinity, the steady state response will evolve. Okay, the attenuation, the gain will be different, and the shift will also be different, and this can be, well, represented graphically, and in this course we'll do this mainly using a Bode diagram. So we have just seen that we can compute the steady state response of a linear system subjected to an input sinusoid at frequency omega as follows, and all that you need is the transfer function of the system. And you can see that the steady state response, steady state means that all transients have disappeared, yields a sine at the same frequency omega over here, but that there is amplification and that there is a phase shift over here. Okay, and this amplification and this phase shift can be obtained from the transfer function when it is considered at s is equal to j omega, right? And this can be represented in the frequency domain, and we'll mainly focus on the Bode diagram. We'll leave these two other representations, the Nyquist diagram, for your information here, and we'll leave also the Black-Nichols diagram for your information. These are covered in courses that are more control oriented, such as the course of my colleague David Rouchard. Okay, so in a Bode diagram, what you do is represent the gain and phase as a function of frequency omega using logarithmic or semi-logarithmic scales. And in a Bode diagram, you actually have two diagrams. You have the amplification, okay, the gain as a function of omega, and you also have the phase shift as a function of omega. So we'll come back to that later, and we'll consider the Bode diagram of a first order system.